Okay, so welcome back everyone to part two of this session. It's my pleasure to introduce Lawk Mineh from Southampton, who will be talking about separability of products of subgroups.
Hello, thank you to the organisers for allowing me the opportunity to speak here. And apologies for in advance. This is kind of an experimental talk, so my hope is to kind of do a bunch of propaganda for this property that's semi-obscure and I'm really interested in, but not very many people know about or maybe care about. But hopefully, I'll tell you today why I find it interesting, why I think it's a cool property, and maybe someone will be inspired to think about it a bit more. So the property is this separability of products of subgroups. So to start off, I should tell you what separability is. And it's really this sort of approximation property. So I have a group, I have a subset, U of that group, and I say that subset is separable if any element outside of the subset, there's a homomorphism down to a finite group, a finite quotient, and the image of that element is distinct from the image of the subset, the group. So you can kind of distinguish the subset from the rest of the group by finite quotients. You can approximate it well. And yeah, there's this list of increasingly strong separability properties that whatever group you're working with could have. And it starts with residual finiteness. So this is essentially the weakest separability property you might ask for. And it says that the trivial subgroup is separable. Yeah. So this is like saying you can distinguish any two elements in the group, any two elements in finite quotients. Much stronger than this is the property of subgroup separability. So uh, your group is called subgroup separable if every finitely generated subgroup is separable. Slightly stronger is the property of double coset separability. So yeah, it's the name's kind of obvious what it means. You take any two finitely generated subgroups, their product is separable. And then once you have this, you can talk about triple cosets, quadruple cosets, whatever takes your fancy. And in the limit, you have this product separability, which you essentially get by replacing 2 in the above definition with n and letting n vary arbitrarily. So this is asking all possible products of all finitely generated subgroups to be separable. And yeah, this is the property that I'm interested in. So why should we care about all this stuff? Firstly, I'll try to give a bit of motivation for separability in general, in case people don't know about it too much. So the general gist is that if you have good separability properties in your group, then you can do lots of things. Like it's a very useful tool. And one thing that illustrates that is the following sort of classical theorem. And it says if you're a finitely presented group and you have a finitely generated subgroup that's separable, then that subgroup has decidable membership problem. So already off the bat, we're getting some quite strong algorithmic consequences from separability. The decidability problem, or even the word problem, is undecidable in general. So how does this go? Well, okay, you take a word in your finite presentation and you want to decide if it's in your subgroup or not. And what you can do is you can run an algorithm, and this you can always do without any separability, that just lists all the words that you can write in your group. And you keep going, you keep enumerating all these words and reducing them down by the finitely many relations. And if your word represents an element of your subgroup, H, then eventually this guy will terminate. Not so if it's not necessarily in the group, in the subgroup. But this is where separability comes in. So separability allows you to you enumerate all the homomorphisms from your group down to finite quotients, which is something you can do because everything's finite. And yeah, if your element isn't in your subgroup, then it's going to fail to vanish. It's going to fail to be in the image of the subgroup in some finite quotient eventually. So you essentially run these two parallel algorithms. One tells you, well, eventually it terminates if your word is an element of the subgroup, and the other one using separability terminates if it isn't. this is an example of a nice way you can use separability to get some consequences. On the more geometrical side, we have this sort of it's a lemma, I guess, but a reformulation of separability, um, sort of geometrically. So imagine we start with a complex X, and we're looking at a subgroup H of the fundamental group of X. Now there's a cover of X corresponding to the subgroup. This is just algebraic topology. Um, and the criterion is that the subgroup is separable in the fundamental group if and only if every compact subset of this intermediate cover um, embeds in a finite sheeted intermediate cover of X. So yeah, you can see how this might be useful. For example, like you can do stuff like promote immersed subcomplexes of X to embedded ones in finite sheeted covers of X. And embedded things they behave much more nicely than immersed things, for example. So this is a nice way that you can use separability to get geometric conclusions. Okay, and I'll talk more about product separability and stuff in a minute. First, I want to give you some examples just to demonstrate that the classes of groups that I told you about a moment ago are non-trivial and not all the same class. So let's see that. Residual finiteness. So I want to give you an idea of how big these classes are. Ooh. Um, so all finally generated linear groups that are residually finite. This is a classic result from Maltsev from I think the 40s or something, very algebraic. Um, and so linear groups form a massive class. Probably most of the groups that are friends with are linear, in fact. Um, but these groups are not necessarily subgroup separable. And I don't know off the top of my head what the simplest example is, but there are, for example, lattices in rank 1 Lie groups with higher dimension, which are not subgroup separable. Uh, so yeah, subgroup separability. Okay, this is a bit more of an artificial example, but it turns out there are certain split extensions of this form. So you've got here a free abelian group acted on by its automorphism, its full automorphism group SLNZ. And then these are subgroup separable for various theoretical reasons, but they're not necessarily double coset separable. And then for double coset separability, there's more natural class of polycyclic groups. So these are the groups that have a subnormal series where all the factor groups are cyclic. Lennox and Wilson actually showed that these are double coset separable back in the 80s, but they're not necessarily triple coset separable. And there's quite simple examples like the Heisenberg group, the integral Heisenberg group, if you know this, is not triple coset separable. So yeah, I want to just say that these properties are satisfied by various familiar classes of groups, and they're sort of subtle. So even like going up from double coset separability to triples is not a trivial thing and not a guarantee. So yeah. Now, what can we say about products? Okay, so there's a trivial example here, in a sense. Finally generated abelian groups are product separable. Now, it's maybe like a easy-ish exercise. You can go away and try to do it. Spend half an hour thinking about it, directly from the definition that finally generated abelian groups are subgroup separable. This is quite easy. And then just the fact that they're abelian means that the product of any finally many subgroups is again a subgroup. So this is true for trivial reasons, but it's a nice example to have in mind. The first non-trivial example actually comes from free groups. So these were shown to be product separable in the 90s by Ribas and Zalewski. And I think it's interesting here to point out the nature of the proof. So Ribas and Zalewski considered actions of free groups on these profinite trees. So these are these wacky spaces that are inverse limits of some finite graphs satisfying some tree-like condition. And yeah, so they studied the convexity properties of these profinite trees, and they get this result. Pushing that result a bit further is Shihong Yu, 97. So he used the same method essentially, but strengthened a bit to show that the direct product of a free group with an infinite cyclic group is product separable as well. The next sort of major result in this area comes from Coolbois. This was in the early noughties, and he showed that free products of product separable groups are product separable. So the property is preserved under free products. And again, I think it's worth pointing out the method of proof here. So Coolbois proceeded with proving this using sort of model theoretic, language theoretic techniques, which are very different to what Reeves and Zalewski is use. I just think it's kind of wacky that these methods apply here as well. And then the next big step, I guess, comes from Ignatian a few years later. So really, he shows something a bit different. I'll talk about it in a future slide. But locally quasi-convex, I should say, subgroup separable hyperbolic groups. And if you don't know what those are, imagine just, for example, surface groups or hyperbolic limit groups, if you know about those. Um, these are product separable as well. And again, here we have a completely different proof method. This really is geometric group theory. You're working with like combinatorial sort of geometry, hyperbolic geometry, and these techniques allow you to get this result. So I think this is kind of something that's stark about this area is there seem to be a lot of tools from lots of different, very diverse things at play, and you can attack it from many angles. So that's something that's interesting. Okay, why should we care about products? Well, aside from the fact that I think just personally it's a very aesthetic condition, like it's maybe you care about subgroup separability, and then it makes sense to ask about these higher structures, bigger products and stuff like that. It has a collection of varied applications, which I think are interesting as well. And the first one comes from this cubulation. So if you're working with a cube complex, say a compact cube complex, then knowing that the fundamental group is double coset separable actually tells you that the complex you're starting with is virtually special. That is, it has a finite sheeted cover that's a special cube complex. And if you don't know what this means, then just think you get lots of incredible algebraic um, consequences from this. For example, the fundamental group of X is going to be Z linear, and it's going to have many retraps onto many nice subgroups and stuff like this. You get very strong algebraic results out of this. And so this was proven by Haglund and Wise in the noughties. Uh, that's cool. Double co-accessibility also appeared in the proof of this so-called strengthened or geometric Hammond-Neumann conjecture. So if you know about the Hammond-Neumann conjecture, this is a really classic conjecture that says if you have two finitely generated subgroups of a free group, they have a particular rank. What does the rank of the intersection look like compared to the rank of the two original subgroups? And so the Hammond conjecture is just a strong bound on this rank. And leaving the setting of free groups, you can talk about Euler characteristics of subgroups, for instance, which is something that coincides with just the free rank in the free group case. And it turns out you can actually prove these sort of strengthened Hammond conjectures in larger classes of groups using double coset separability. This appears as an important step in the proof. It's not a whole deal, but it's important for it. And so this was done by, I should say, Heiken Zapirin as well. I forgot to mention that, but Sam Fisher and Ismael Morales recently did some work on this for limit groups and certain graphs of groups, for instance. Moving on to higher products. So product separability initially, one of the initial motivations for actually showing that some groups are product separable comes from actually a conjecture in semigroup theory, which is interesting. It's very different to what we usually think about in group theory. So there was this big conjecture called the Rhodes type 2 conjecture in semigroup theory, and it's about computing a particular really important submonoid of submonoid, a given monoid or semigroup. And it turns out there's a sequence of fairly complicated reductions you can do to show that computing this particular submodel is uh, well, you can do that by knowing that products are separable in the free group. So this is work with Pin and Reutenau in the 80s, and then it was resolved by Rubin and Zaleski, who showed that free groups are product separable. Um, Neat. And finally, I want to mention these generalizations of Rashofsky's theorem. So what is Rashofsky's theorem? It's this classic theorem in graph theory about partial automorphisms. And what does it say? It says, okay, I've got a finite graph gamma. I've got a partial automorphism of that graph. So this is an isomorphism of two subgraphs, essentially, of gamma. Um, the theorem says that you can extend this graph. So there's a bigger graph, gamma hat, say, containing gamma as a induced subgraph, a proper induced subgraph. And this automorphism, or the partial automorphism of gamma, actually extends to a full graph automorphism of this bigger graph. So you can always have some vertices and edges, maybe lots and lots and lots. The graph can be very big, but you can extend partial automorphisms to actual automorphisms. And yeah, so Rashofsky originally proved this using, I think, probabilistic methods, uh, which is big in combinatorics. But it turns out there's a proof of this using product separability in free groups. And this was due to Herwig and Laskar. And they showed that you can, in fact, stick a whole bunch of adjectives in there. So you can, for example, insist that your original graph gamma is triangle free, doesn't contain any induced triangles. And if you do this, you can actually construct this bigger graph in such a way that it's also triangle free. And you can do this with square free and all sorts of things, like add a whole bunch of adjectives you like. Um, in fact, what they prove is something far stronger, but not something that I know a whole lot about. So they prove this extension of partial automorphisms property for in a very model theoretic setting. So they show that using product separability, that if you've got some finite L structure, okay, L is some finite relational language, so just some symbols and some operations and relations on those. Um, and okay, so you've got T free here, so T is some collection of L structures as well, and you're saying that um, M doesn't represent these very faithfully in a sense. I won't talk about that. But yeah, so you've got these L structures, and it turns out you've if you have a partial automorphism of these L structures, which are a language theoretic model theoretic thing, you can always extend them to full automorphisms of bigger finite L structures. Okay, so that's maybe a bit heady, but there's also a more geometric group theory uh, result in this vein quite recently. So Abdendi and Wise, I should say also all this Herwig and Laskar results were from the early 2000s. Just last year, though, Abdendi and Wise showed one of these extension of partial automorphisms results for cube complexes. So they tell you if you start with a compact cube complex and you have a partial local isometry of that cube complex, then it extends to a full automorphism of a bigger compact cube complex containing your original one as a locally isometrically embedded subcomplex. And in fact, if you throw in the adjective special here, uh, you can actually arrange it so that the bigger complex is also special. So that's neat. And it turns out they use separability of up until like quintuple cosets or something like this to get this result, which is pretty wacky. But yeah, onto some work that I've done in this area. I want to mention. Um, okay, so I won't go into what hyperbolic groups are and what they're all about, but you should just think of them as nice groups with some sort of negative curvature condition. So hyperbolic groups are groups where the Cayley graphs are hyperbolic as metric spaces. So they're kind of like fattened trees in some way. And I'm interested in this sort of the Topeka condition of relative hyperbolicity. So this is I'm really not going to explain this, but a group is hyperbolic relative to some collection of subgroups. if maybe the whole group isn't hyperbolic on the nose, you've got these bad subgroups H lambda, which can cause you trouble. Um, but if you forget about what's happening in those and look at the relative Cayley graph, whatever that is, instead of the actual normal Cayley graph, then this is hyperbolic. And also some technical condition is satisfied, which I'm not going to talk about, but I don't want to lie to you, so I've written that in as well. And yeah, so there was this result of Minassian, which I mentioned earlier, which for hyperbolic groups, it's a version of product separability for hyperbolic groups, and it says that products of quasi-convex subgroups are separable in Q-sub hyperbolic groups. So I'll say what this means in a minute. So quasi-convex subgroups, they're a subclass of all the finitely generated subgroups of a hyperbolic group. And you can think of them as essentially the sufficiently nice geometrically uh, subgroups of hyperbolic groups. Um, so yeah, and what this Q-sub condition is saying is uh, the individual subgroups. So it's like subgroup separability, but instead of all finally generated subgroups are separable, just all the quasi-convex subgroups are separable. And you kind of need this condition as a basis of induction when you're doing the proof. So it's a um, necessary thing. Yeah, so what have I done? So in joint work with Charlotte Manassian a couple of years ago, we generalized this to the relatively hyperbolic setting. So we showed that if you've got a relatively hyperbolic group, which is Q-surf, and the bad subgroups product separable, then if you have any product of relatively finely generated, relatively quasi-convex subgroups, again, I won't say what exactly this means, but maybe you get the vague idea of what's going on here. Products of these guys are separable. Okay, so that's a bit of a mouthful. I want to try and give a bit of context to this using this following diagram. So this is a commutative diagram of generalizations here. In the top left corner, we have free groups. This is the first guy. So free groups are exactly the groups that act, finally generated free groups act freely and co-compactly on trees, actual trees. And these we know are product separable. You can generalize this in one sense to free products. Um, Free products are exactly the groups that act not freely on trees, but edge freely. So the edge stabilizers are trivial, but you maybe have some vertex stabilizers. And in fact, the vertex stabilizers are exactly the conjugates of the free factors. And you can think of them as like the bad subgroups. You know, it's not completely free, but you've got these free factors, which can be as bad as you like. And Kuhlbar showed that as long as these bad subgroups, these free factors are product separable, then the free products are product separable. On the other hand, you can generalize this action to hyperbolic groups. You can try to coarsify a bit. So hyperbolic groups are exactly the groups that act maybe not freely, but coarsely freely. So properly discontinuously on hyperbolic graphs. So these are like fattened trees in a sense. And yeah, so the result I stated on the previous slide said that products of quasi-convex subgroups are separable here. And this is exactly the analog. So in a free group, these are hyperbolic, and the finally generated subgroups exactly coincide with the quasi-convex subgroups. That's not the case in a general hyperbolic group. So it's like a generalization in this sense. You work with what you have, which is the nice subgroups. But in a free group, all the subgroups are nice. And these guys admit this common generalization in relatively hyperbolic groups. So these groups are relatively hyperbolic groups are the groups that act sort of edge properly on hyperbolic graphs. So they act on fattened trees and they have some vertex stabilizers, but the edge stabilizers aren't very big in a sense. Yeah, and the vertex stabilizers correspond exactly to the bad subgroups again. And yeah, so we exactly expect the result that I had on the previous slide that as long as the bad subgroups, the vertex stabilizers are nice, then products of the convex subgroups, the nice subgroups of relatively hyperbolic groups are separable. And in fact, using this, we actually obtain product separability on the nose for quite a few classes of groups. So we showed that the following groups are product separable. Limit groups. So these are groups that play a role in the sort of the logic of groups in a sense. They were introduced by not introduced. They've been studied for a long time, but a lot of work on them was done by Zilosela and Kalantovich and Myasnikov. And you can think of them as sort of limits of free groups in a given a certain metric on the space of all groups. And these groups are product separable. We also showed that finitely generated declining groups are separable. So these are the finitely generated subgroups, discrete subgroups of isometries of the hyperbolic free space. And this actually uses some deep results in free manifold theory to get this. But we have this as well. And then lastly, fundamental groups of graphs of free groups or cyclic edge groups. Okay, if you don't know what graphs of groups are, you should just think of, okay, I've taken a bunch of free groups and I'm gluing them together along some cyclic subgroups in some way. And as long as they're balanced, I'm not going to say what this means, but not being balanced is an obvious obstruction to any sort of separability conditions. As long as they're balanced, you have some basic separability conditions, you actually get product separability for these groups as well. Yeah, I just want to cap off with talking about some future work. So the following is a bit of a work in progress. I'm not being too ambitious. Let's say 25 plus is coming out sometime next year or beyond that. I'm thinking about extensions. It turns out, so what we've got so far is that if you start with a nice enough hyperbolic group, you can take a direct product with any free abelian group or finitely generated abelian group, and this is still product separable. And this is in some sense like the most basic type of extension. Like it's a split central extension. And I'm really thinking about extensions here. So hopefully there are more better, nicer extensions to come. But I don't want to be too brash about what's existing. And lastly, I want to just round off by mentioning a similar result to some of ours, Sam Shepherd. Just a bit of a shout out. So he showed this result for cubical groups. So if you've got, this is a couple of years ago, if you've got a compact, this should say virtually special cube complex, if you've got some compact virtually special cube complex, then triple cosets of any free convex subgroups in the fundamental group are separable. So you have these convex subgroups that are nice subgroups, and maybe you don't have all the possible cosets, but triple cosets are separable. I think, I don't know, probably in the future, sometime, all the cosets are to come. Yeah, that's pretty much all I want to say. So thank you for listening. Yeah.
Great, thanks, Luke. If we can thank our speaker. Do we have any questions? Feel free to either put something in the comments or if you want to unmute. I'll maybe ask one. I'm going to email you, like, by the way, about the semi-group thing, but I'll do that later.
Okay, sure.
But my question is, so if I've understood correctly, free groups and free abelian are product separable.
That's right.
RAGs? Question mark?
We don't know. So, I mean, I suppose, yeah, so we don't even know that, okay, I suppose it follows from this result, but like a product of a free group and a free abelian group is kind of hard already. Like it's yeah, rugs are a long way away.
Yeah.
But there are some. So there was a result. Me and Davide Spriano showed that I think the product of stable subgroups of rugs or something like this is separable. But I should check.
Cool. Okay. Nice.
Yeah, strongly quasi-convex. That's right. Yeah, strongly quasi-convex subgroups of rugs. Products of those are separable.
Okay. Cool. Any final questions?
I have a question. These properties of like double coset separable, triple coset separable, etc., etc. Are there examples that show that all of these properties are distinct?
No. So the best we have is double coset does not mean triple coset separable. Beyond triple cosets, I'm not entirely sure. I don't think there's not a strong theoretical reason to believe that they shouldn't be all distinct. Like probably they're all distinct. Like triple coset shouldn't imply quadruple coset and so on and so on. But also on the other hand, in my mind, there's some sort of distinction. Like up to double cosets, you're still dealing with like group operations, which are essentially like two-sided, right? Beyond that, you've got like triples and quadruples, and somehow they have a completely different character to them. So it's possible that there's no groups that are triple coset separable and not product separable, but that's not known.
Okay, interesting. Thank you.
When you use
Oh, sorry, Ollie.
sorry, sorry. When you use or when applications use product separability for something, are they usually using like the full force of product separability, or do they just have some high number that they need
Yeah, some high
up
number. So I
to,
think
and they're just using that?
the highest I've seen is quintuple cosets, and that's in this result of Abdendian Wise, which is here. So I don't know. I've been thinking about this recently. Like, you usually use product separability as like somehow there's some conditions that you can encode in a multiple coset, and you're trying. These are some sort of like bad conditions, and you're trying to avoid them, and you use separability to sort of avoid them in some finite cover or something like this. Um, so if you had something like um, yes, these multiple coset conditions, if you used multiple cosets for any length, you'd be encoding maybe arbitrarily complicated conditions, which I don't know, maybe it's something you want to do in some applications, but it's um, yeah. Oh, actually, so product separability in the full force of product separability was actually used for the semigroups conjecture. But yeah, for all the other ones, it's just like two cosets, three cosets, four cosets, five cosets, and I haven't seen higher than that.
Thank you.
Welcome.
Okay, let's thank our speaker one last time.